Good morning, everybody. Welcome to this third technical workshop titled the Uraba, Sinu, San Jacinto Mega Areas. Before starting the talk this morning, I would like to mention some announcements. And we apologize because the previous presentations, number 1 and number 2, I'm talking about April 9th and April 16th, have not been loaded in the website. Basically, we are facing some conversation with the, we are facing some problems with the boundaries of the rocks in the Caribbean and in the Caribbean Sea, and we are still discussing those boundaries with the institution in charge of that in Colombia. But as soon as that problem is solved, for sure, the couple of sessions will be put in the website of the agency. We also would like to say that we, besides having the people involved in the Play Fairways project last year, plus the interpreters of the ANH, we have had the chance to invite some speakers to our weekly talks. So in this case, this week we have Freddy Corredor, and in the talk of the Middle MAC on May 7, we will have Ivan Olaya. As well, we will have Ivan Olaya on June 4, when we will discuss the Pacific, the opportunities in the Pacific offshore. If anybody would like to be part of this effort, and if somebody wants to talk or give us a talk to us here as part of this workshop, please let me know. Send me a note to my email, jose.diarmas@anh.gov.co. Okay, today we have the pleasure to have with us the following talks. I mean, we have from 8 to 9, we have the Geological Integration, Petroleum System and Prospectivity of the Colombian Frontier Basins, Uraba, Sinu, San Jacinto, and San Jorge, and is going to be given by the group of the Universidad de Caldas. From 9 to 9:30, we will have the talk titled Shale Tectonics in the onshore Sinu Basin, Northern Colombia, implication for the interpretation of structural traps and hydrocarbons exploration. That talk is going to be given by Geostrap, which director is Freddy Corredor. And from 9:30 to 10, the agency is going to close the topic and with the talk exploration opportunities in the Sinu San Jacinto Basin, given by Daniel Rodriguez for ANH Interpreter. Let me just, before giving the chance to talk to the Universidad de Caldas, give you some backgrounds of the people, of the speakers. This morning, we have Enrique Velázquez. Enrique Velázquez is a geologist of the National University of Colombia, graduated in 1978. Enrique has a degree in business administration from the EAN University. Also, he has a degree in advanced management from the Universidad de los Andes in Colombia. More than 40 years of experience working for Texaco, ExxonMobil, Inal, Cipetrol, Ocol, Oxy, Ecopetrol, Geopark, and Hunt Oil. Enrique was the international exploration manager and exploration vice president of Ecopetrol. Currently, Enrique is director of the Geological Integration projects of the University of Caldas for the ANH. With Enrique, we have as well Andres Pardo, who is a geologist from the Caldas University, graduated in 1988, Master Science in Vegetal Micropaleontology, and PhD in Science of the Liège University, Belgium, in 2004. Andres is professor in the Department of Geological Science of the Department of Geological Science in Sedimentology, Regional Geology, Palynology, and Field Geology. Since 1989, he has been a professor there. He was advisor for the ANH from 2006 to 2009. Currently, he is also the director of the Instituto de Investigaciones en Stratigrafía, IES, and also he is the research group director in stratigraphy and volcanology in the Universidad de Caldas. We have also with the Caldas University, Roberto Linares, geologist as well from the National University of Colombia, graduated in 1987, Master Science of from the University of Colorado, USA, PhD candidate from the Universidad of Calgary, Canada, more than 30 years of experience working for Ecopetrol, Pocol, BP, and Equion as a seismic interpreter and structural geologist. And the last person in this group is Cesar Mora, geologist with more than 33 years of experience in basin analysis and prospect evaluation, play concept assessments, petroleum system modeling, petroleum geochemistry, and yet to find assessments. He has been involved in regional studies in Colombia, Ecuador, Peru, Chile, and Mexico. He has worked for companies such as Ecopetrol, Cipetrol, GEMS, and Cuenca. He's also professor of petroleum geochemistry and basin modeling. Those are the group of the Universidad Nacional, Universidad de Caldas. And we have here as well Freddy Corredor, who is going to give us the second talk. Freddy Corredor is a professional geologist, explorationist, and entrepreneur with over 25 years of experience in the upstream oil and gas industry. He holds a bachelor degree in geology from the National University of Colombia. He was graduated in 1994. He also has a master's science degree in geology from the University of Colorado at Boulder and a PhD candidate in Earth and Planetary Sciences from Harvard University. He started his professional career with Occidental Oil and Gas in Colombia. In 1999, he moved to the USA to pursue postgraduate studies. During that time, he held summer internship positions with Oxy, Chevron, BP, and Shale. In 2004, he joined Shale Exploration and Production Company in New Orleans as senior structural geologist for the Gulf of Mexico. In 2006, he returned to the country, to Colombia, and he has had several positions. He is the founder and director of GeoStrap, SAS. He has been also director of new ventures in Latin America for Casa Exploration. He has been also the exploration manager of Petra in Colombia. And the most recent assignment was execute BP exploration of American resources. And the final talk on behalf of the agency is going to be given by Daniel Rodriguez, who is a geologist from the National University, graduated in 2017. He has a master's science in exploration geophysics from Leeds University, England, in 2018. He has more than 3 years of experience working for Oxy and in the last couple of years with the ANH. Okay, so now we are going to give the word to Enrique Velasquez in our first talk.
Okay, good morning, ladies and gentlemen. I would like to thank the National Hydrocarbon Agency for inviting us to present the work, Geological Integration, Petroleum Systems, and Prospectivity of Colombia's Frontier Basin Sinu San Jacinto, and San Jorge Subbasin in the lower Magdalena Valley. I would also like to commend the ANH for creating opportunities for the oil industry and university to work as a team, blending the pragmatism of the industry with the academic excellence of the University of Caldas, which helps to produce high quality products like this one that we're going to present. The way that we're going to conduct the presentation, we are 4 guys in the presentation, but let me tell you that the whole team was composed of more than 30 geologists from different disciplines, a lot of guys from experience from the industry, and a lot of excellent people from the University of Caldas. We started with stratigraphy, then we jumped to structural geologists, and then Cesar Mora will complete and finish Petroleum Systems. At the end, if we have some time, I will address some important conclusions. Hopefully, we have some time to answer your question. Okay, so let's start with stratigraphy. Okay, we'll conduct it by Dr. Andres Pardo. Okay, Andres, go ahead.
Hello, thank you, Enrique. Hello, everybody. Thank you, ANH, for the opportunity. As Enrique mentioned, this work was performed by 22 geologists from the industry and academy. And the first part, we made a compilation of the geological and stratigraphic information of the basins. Here we have in the upper part of the slide a general tectonic framework, and in red dots we have the location of the basins. As you can see, the Caribbean plate, South American plate, and Panama Choco block are 3 main tectonic structures that are in confluence in this area and control the sedimentation and tectonics from the late Cretaceous to recent times. In this map, you can see the location of the basin. This is the Sinu San Jacinto, which is formed by a fault belt with a north-northeast trend direction, with folds and faults. As you can see in the stratigraphy, the Paleogene is outcropping in some parts of the San Jacinto fault belt. To the east, we have the lower Magdalena Valley Basin, divided by the Plato subbasin and the San Jorge subbasin to the south, separated by the Magangue-Sicuco structural height. In this area, last week we talked about Sinu offshore. It's part of the basin. It's a continuation of the fault belts in the onshore. We study the stratigraphy using seismic geology, surface geology, and the information of wells that you can see in this picture. The blue wells have biostratigraphic information, and with this we review all the biostratigraphy and the lithostratigraphy, and also we include more than 20 wells drilled by the ANH in the last 12 years. We study the sedimentology, biostratigraphy, and many properties of the rocks. With all of this information, we construct the 4 stratigraphic, chronostratigraphic charts. You can see the location. The C1 is the strike section parallel to the San Jacinto fault belt, and this, to the south is crossing the Sinu fault belt. And 3 deep sections, the C2 in the upper, the north, in the middle, and in the south in the Uraba basin. We can see, I will show you especially the C1 and C3 cross sections. The first one is this section is or a chronostratigraphic card is composed by 24 wells, 16 from the ANH, and we construct the major on the main stratigraphy. It's important to mention that in green we have the basement composed by volcanic rocks. In gray we have the mudstones. Orange the conglomerates. In yellow the sandstones, and in blue the limestones. As this chronostratigraphic map, you can see the major unconformities between the late Cretaceous and the upper Cretaceous, uppermost Cretaceous. The Canzona Formation is composed by mudstones and micritic limestones, which the geochemical data show that is a good source rock, oil source rock. The upper part over this unit in unconformity, we have a mud-dominated unit. It's not well studied, but it has a good quality for oil production in the Eocene and probably the Paleocene. And over this unit, the conglomerates and sandstone from the San Cayetano unit, which was accumulated during the late Paleocene, lower or early Eocene, accumulated in fan deltas and turbiditic fans. During the middle Eocene and late Eocene, we have a mix of terrigenous, coarse grain terrigenous from the fan deltas like Mako, and mudstones and limestones, which were accumulated in different parts of the fan deltas and platform. To the upper part in the late Eocene and early Oligocene, we have a Chalan-Chengue system and Tolu Viejo, composed by a mixed limestones and mudstone and sandstone. And starting from the Oligocene to the early Miocene, we have a deltaic system named Ciénaga de Oro to the south, and to the north probably the Carmen is a important oil reservoir in the basin. And in the early Miocene to the Pliocene, we have a progradation system starting from Porquero in an important flooding surface, a regional flooding surface in the basin, and to the upper part, progradation of fluvial and deltaic systems. The perpendicular to this card, we have this this location from starting from San Jorge to Sinu offshore basin. We can see the stratigraphy in the San Jorge basin. The basement is mainly continental basement composed by igneous, metamorphic, Permian, Triassic rocks, Jurassic volcanics, and some Cretaceous plutons, granitoids. The sedimentation in this area is starting probably in the late Eocene, Oligocene, but is early in the northern part, especially in the plateau deposcente. In the San Jacinto basin, or Sinu San Jacinto fault belt, we can recognize an important unconformity, which spans from the late Eocene until lower Miocene. And it's controlled the sedimentation, the formation in this area during this period of time. And the Sinu offshore basin is not well known, as I mentioned last week, in the talk last week, because there are no deep wells that drill all the sequence. In this convention, we remark the presence of mud diapirs, which are very common in the San Jacinto, in the Sinu belt. With all of this information, we construct the Paleogeographic cards. And I will show these general cards, which were constructed with these yellow points represent the wells or outcrops which were based the cards. In dark gray, we have the deep marine environments. In light gray, the shallow marine. In yellow, the coastal. In white, fluvial. And in orange, the fan deltas and turbiditic fans. And in brown, we have the emerged areas with erosion. During the Campanian Maastrichtian, the Canzona formation was accumulated probably in the deep marine environments in the north of the basin. And to the south, we have emerged other areas with submarine fans, as we can demonstrate in the Western Cordillera, nowadays in the Western Cordillera of Colombia. During the Paleocene, late Paleocene, early Eocene, we have all the basement of the lower Magdalena valleys emerged, and some coastal and deep water submarine fans were developed in a tectonic active system. As you can see to the east, all the fluvial system from the Barco, Los Cuervos, and Cerrejón formation and coastal to the north was development in this area. During the Middle Eocene, late Eocene, we have that the plateau depot center to the north of Lower Magdalena Valley start to fill with fine-grained sediments in a restrict bay. And to the south, we have a depositional system, especially with delta, fan delta, and a mixed carbonate and terbigenous platform. During the Oligocene, we can see that the coastline start to move to the southeast, and the Magangesi-Cuco High control the sedimentation and divide the upper part, the northern part in the plateau, and the southern part in the San Jorge Basin. You can see some carbonates were development in this period. In the lower Miocene, you can see that the coastline continued to go to the southeast, and the development of important riffle carbonates in the Sicuco High. And another important thing in this period is in the San Jacinto fault bed start to be deformed, and some of the previous accumulated sedimentary units start to be reworked. In the middle Miocene, we have the maximum, in the lower middle Miocene, the maximum transgression, and probably the major systems, fluvial systems, start to act to be development to the north, and it means that during the late Miocene and the Pliocene, all the fluvial systems were progressing to the north. The Magdalena submarine fans start to develop, and some turbiditic system in the offshore basin. This, as you can see in my presentation of the distribution of the sandstones, this geology or this stratigraphy control the presence and the position of the reservoirs and the source rocks. This is all the information about stratigraphy. Roberto will present the part of structural geology. Roberto, it's yours.
Okay, thank you, Andres. Good morning, everybody. So in the following slides, I will show you the result, a summary of the result of the seismic interpretation and the structural modeling done in the basin. This first part, I mean the seismic interpretation was carried out by a group of interpreters led by the geologist Jose Urueta. And then, at the final of this part of the presentation, I will show you the main structural feature that we found in the basin. These two jobs were done in an interactive way. I mean, the seismic interpretation was the main input of the structural modeling, and in the same way, the result that we interpreted in the transect was an input in the seismic interpretation. So in this first slide, on the left, you can see the location of the wells were in this interpretation. In
Roberto.
green.
Roberto, pon
Yes.
modo presentación.
Modo presentación, sí.
Está en modo presentación.
Ah, sí,
No,
es por lo que tiene dos
Ve
pantallas.
opciones de presentación. Ahí en tu PowerPoint dice opciones de presentación. Arriba a la izquierda. No, en PowerPoint, Roberto. Donde estabas en tu ventana de PowerPoint, vuélvela a poner. Ahí dice arriba a la izquierda opciones de presentación. Y ahí dale cambiar vista moderador. Ahí.
Okay, ready?
Ya, perfecto.
Okay, thank you. So I will say that the interpretation was used about 18,000 kilometers of 2D seismic, 2,000 of 3D seismic square kilometers, a total of wells of about 300 wells, and of these 300, 61 of them has a check shot information. The check shot, the wells with check shot are in yellow color in the map on the left. On the right, you can see the location of the seismic data used in this interpretation. Now I will show you some of the examples of the interpretation. In the upper part, you can see the north composite section that is located in the map. You can see the location on the right. You can see here the different sequence. The basement is in purple color, and the overboard and the stratigraphic, the sedimentary sequence are in different color of yellow and orange color. This part is the Eocene and Pliocene sequence. The Oligocene is in orange color. The Miocene is in this yellow color, in this light color, and the upper part is the Pliocene and the recent. The main structural features are this kind of reverse fault. Many of them are tectonically inverted, and there are many opportunities located in the high wall, in the anticlines in the high wall of this reverse fault that bears to the northwest. At the bottom, you can see the south sector composite section is located. You can see here the location of this composite section. In the northwestern border, you can see the typical tectonic of the mud volcanism that is characterized in the Sinu onshore, that this intrusion of the mud create this kind of deformation in the sedimentary sequence, creating opportunities in the same fashion that you can see in salt tectonics, where you have reservoir against this mud. Here is the geometry of the San Jacinto fault belt. that is characterized by reverse fault with high, more vertical fault planes, that this fault affected the basement and the sedimentary sequence. Against in the same situation in the north, many structural tabs are created in the hang wall of this fault. Regarding the San Jorge Sub-Basin, we have the deep composite section that is located in this part near the boundary between the San Jorge Sub-Basin and Plato Sub-Basin. Again, this is the typical deformation in the San Jacinto fault belt with a almost vertical reverse fault that affect the basement and the overburden. The San Jorge Basin is less deformed. However, there are some important reverse faults with that bears to the southeast and affect the basement and the tertiary sedimentary sequence. There are many these minor reverse faults that also create minor opportunities, but could be important in determine what is the potential of these minor faults that affect mainly the basement. At the bottom, you can see the strike section going from south to north to the right, and you can see the geometry along this direction. Again, the interpretation, the formation is characterized by this old normal fault. It's interesting to see that this normal fault that should have northeast, southwest, northwest, southeast direction are not tectonically inverted as those in the perpendicular direction. The interpretation of this is that these fault planes are in the today direction of the main stress. The main outcome of this interpretation are the structural traps. In this slide, you can see the map from the basement, the H1 sequence that corresponds to the Paleocene to the Eocene, and the H2 sequence that corresponds to Oligocene.
Use el pointer, porfa.
Regarding the basement, you can see that in the San Jacinto fault belt, we have the shallowest position of the basement, as well as in the south part of the San Jorge sub-basin. We have some deposit here in the Sinu onshore and in the south part of the San Jorge basin. The geometry of the H1 and H2 sequence is quite similar, and these sequence are just deposited in the San Jacinto fault belt. You can see the highest structural position with orange and yellow color, and the lowest one in blue colors. These three maps are the geometry represent the geometry of the H3 to H5 sequence, which correspond to the early Oligocene to Pliocene. Again, these sequence are deposited in the San Jorge basin, as you can see, with the epicenter in the near the boundary between the San Jorge and Plato basin. This blue color represent that epicenter. Now I will talk about the place that we determined in this study. This is the Sinu onshore, where you can see again the mud volcanism that is affected the stratigraphic sequence, the sedimentary sequence, and create this fault that creates some options in the same type that we could find in the salt tectonic, where we have some reservoir against this mud. So this is important plate that is unexplored. We have in Sinu and San Jacinto this kind of stratigraphic plate type where we have the sediment of the Miocene overlapping against the basement. On the right, you can see the same kind of type, this kind of overlaps termination of the Oligocene sequence against the Eocene sediments. We also have in this basin a structural plate type, plate traps like this, reservoir located in the high wall of this reverse fault and in the crest of the anticlines. Regarding the San Jorge subbasin, we have both stratigraphic plays and structural plays. Talking about the stratigraphic plays, we have this kind of truncation termination of the porquero of the unit of the porquero against the base of the Tubara unit, and the overlap termination of the at the lower sequence of the porquero formation against the Ciénaga de Oro unit. Now on the right, you can see the structural plates that we determined in this study. In the upper part, we have the crest of the anticline located in the hanging wall of this reverse fault, and also we have in the foot wall of this normal fault that remain that don't have any tectonic inversion effect. That we have this kind of position in this position, and here interesting place to be explored in the future. Now, in the second part of this presentation, I will talk about the structural model. In order to understand the structural model of these basins, we constructed 12 sections, 3 deep sections and 3 in strike direction, using, as I said before, the seismic data, the information from 60 wells, surface geology, and gravimetry. The length of this cross section were between 140 kilometers until 372 kilometers long. The location of the transect are located here, and the well used in this study are in green color. The gravimetry was an important input in order to understand the position and the depth of the basement. So here are the location of the transect and the geometry of the basement. This is information taken from the ANH in 2010. Using this information in this study, in the 2010 study, was calculated the depth of the basement. So the different in transect took in account these values of the depth of the basement. This is important point to determine if the fault affect or not the basement, and also if this is a thin skin tectonic or thick tectonic events. These 3 sections are just example of the 12 constructed. In the upper part, you can see the transect number 5 that is located in this position in the south of the study area, going from the Sinu onshore. This is the San Jacinto thrust belt and the San Jorge subbase. Again, you can see the mud volcanism and the geometry that the fault and fault that affect the San Jacinto belt. As I said before, many of the reverse fault are vertical, The boundary between the San Jacinto fault belt and the Sinu is this huge river fault, the Sinu fault. And in the San Jorge, we have this minor deformation characterized mainly by this all normal fault, many of them tectonically inverted and leaving some opportunities in highest structural point located here or this that are already have been already drilled. Then we have the transect number 10 that is located in the southern part of the study area. Again, this is the kind of geometry of the more diapers. As I said before, creating a deformation in the sedimentary sequence, creating at surface this kind of wide synclines at tight anticlines. Many of them are related to this reverse fault and with the oil seeps and gas seeps at surface. Again, the geometry of the formation is characterized by this reverse fault that affect mainly the basement and part of the overboard. At the bottom, you can see the geometry along a strike from south to north. The location is located here on the map. This is the one of the shallower part of the San Jorge Basin. And we have seen that the plateau is deeper than San Jorge. In this direction, as I said in the seismic interpretation part, there are many normal faults that don't show any kind of tectonic inversion, and many of minor faults that affect mainly the sedimentary sequence. So before ending this presentation, I just to mention that the potential of this basin are huge. There are many opportunities related to the place that I explained, opportunities in the stratigraphic and structural traps. So the potential for this the potential is huge, and there are many reserved and unexplored. So now I'll give the floor to Cesar. Thank you.
Gracias, Roberto. ¿Dejas de compartir, por favor?
Listo.
Okay, good morning, everyone. Now we are going to talk about petroleum systems, about the play fairway analysis, and finally the jet to find we did for these basins. First point we want to code is related with the hydrocarbon occurrence in these basins. In the Sinu San Jacinto Basin, we have a lot of oil seeps and gas seeps, and we have some oil coming from some wells from the subsurface. The most important thing about these oil seeps could be that we can prove the option to have black oils, gas, and condensate. We had all these kind of oils, and also using the geochemical information from these seeps, we know, or we can see that we have at least two different source rock intervals. One of these is related with a marine platform. It's something like the La Luna formation environment that in this case could be Canzona formation. And the other one is related with marine deltaic source rock, probably from the tertiary. That information is very important for us because not just because it's the proof that we have an active petroleum systems, but also because it's very important to calibrate our basin modeling. In the San Jorge area, we have, excuse me, here in the San Jorge area, we have a field with a gas field. That's the only subsurface hydrocarbon occurrence we have in the basin. Talking about the source rock, first point is that we had information that show that most of the source of the sedimentary intervals that were analyzed in the past represent or are coming from marine sequence, but really we don't have source rock intervals on that units. But also we can see here that we have an important number of samples coming from the Canzona Formation and from the Eocene and maybe Oligocene sequence, where we have a very high hydrocarbon potential, a very high genetic potential from the pyrolysis and very high TOC. Remember that we were talking about the quality of the oils, the geochemical characterization of the oils from the oil seeps. Then just thinking in the geological model, we can think in a very simple model where some of the oil are coming from Canzona Formation and others are coming from the tertiary source rock. In this graph, we are showing a very important information that was getting from the ANH. This data are coming from a project that the ANH developed with the Utah University maybe 5 years ago. And this sequence here is coming from the Tierra Alta 2 well. And this probably, or according to the biostratigraphy or chronostratigraphy framework, for the basin, this could be the Eocene sequence, maybe San Jacinto formation. And here you can see at least 300, this green one, 300 of very good source rock intervals. You can see the values for the TOC, the values, the high values for the genetic potential, and the values for the hydrogen index. And also we have another intervals where the potential is high. It's not too high like this, but anyway, we can get oil from here. That means that this interval, the Eocene interval, could be really very important in the basin for the prospectivity and in terms of the amount of hydrocarbon that was generated in the basin. Next step was to do a 1D basin modeling with the multi-1D. Here I'm going to show the results of this well. This is Tierra Alta 2, the well that we were talking about, the source rocks. And here, according with the thermal model, the burial history we use for that point, you can see that the thermal evolution maturity level of the source rock interval is into the oil window, and the Cretaceous source rock is very close to the gas window. According, or as a result of this model, the transformation ratio and the expulsion efficiency is very high for the Cretaceous and is lower for the tertiary source rock. But we have to remember that here we are not in the deepest part of the basin. When we go to the deepest part and we did this kind of model, all the sequence, the source rock intervals are today into the gas window. That means that we have the option to explain all the oil and gas that we have coming from the wells and coming from the oil seeps and the gas seeps. Next step was to do a 3D basin modeling using the geological model, the interpretation, the seismic interpretation, the structural maps that we got from the seismic interpretation group. And we had at least three different results. The first one was the possibility to define the pod active of source rock in the basin. We defined at least 4. The biggest one is located in the southern part of the basin, and this area corresponds to the mud volcanism, and is probably one of the best options to find oil in this basin. We have another 2 productive soft rock, smaller, that are located, one in the Morrosquillo area and the other one in the northern part of the basin. And also we had this other productive of source rock, which is very important because now we know that this is connected, probably connected with this productive of source rock, the huge one that we have in the Plateau Basin. And also we did migration models and hydrocarbon charge model for every one of the reservoirs that were mapped in the project. Here you can see 2 examples, one for the Oligocene, probably something like Ciénaga de Oro formation, lower Ciénaga de Oro, and the other one for early Miocene. You can see different migration types, but also you can see so many accumulation, the green one for oil and the red one for gas, that we define using all this information coming from the geological and geochemical model. One of the things that we have to do, to say is that because of the tectonic model, because of the tectonic evolution of the San Jacinto fault belt, we don't have the reservoirs across the entire area. Then in the prospectivity will be very important to define this kind of boundaries for that units. And it will be very, very important in the mud diapiris area, because here we don't have a very good continuity of the reservoirs. Probably in these areas will be necessary to get a very good seismic, a new seismic program. So, because right now it's not easy to define that boundaries using especially because the quality of the seismic we have here. In the San Jorge Basin, was possible to complete a 3D modeling and was possible to map the productive of source rock for an hypothetical tertiary source rock that we include into the Ciénaga de Oro formation. We don't have direct evidence. We don't have data. We don't have wells showing that source rock, but we have to explain this gas and some oil, some condensate that was reported for this area in some wells. Then we have this model, and according to that model, we got the oil window in the deepest part of the basin. We are at the end of the oil window according to the model, and with that model we can calibrate the oil, but it's not easy to calibrate some of the gases. That means in this basin we need to work a little bit more, especially because we don't have enough information for the deepest part of the basin. According to the model, to the migration model and the charge model, you can see that we have for the Ciénaga de Oro formation, which is the main reservoir here in the Hobo Tablon area, we have so many traps that were charged with oil, someone with oil, someone with gas, and that means that we have the opportunity to find additional oil in place or gas in place in the basin. And last part of this exercise was to put everything together, trying to define some play fairway maps, thinking in the trap, reservoir, and geometry, and thinking in the hydrocarbon charge probability. And those are the results. For Sinu and Jacinto, you can see that we propose 4 areas. The in the southern part, we have this play that we call the Sinu play. This place is mainly related with the mud diappears, and we believe that we have a very great opportunity here because we have oil in the oil seeps. We have sun oil coming from this small field, Santo 1. We have the source rock involved in all this area, and also we know we have reservoirs that were affected, maybe creating a very good traps in the area. Then we have this southern part of the San Jacinto fault belt where we have some accumulation. We don't have too much, especially because the tectonic evolution of this area, or because that tectonic evolution, we lose some of of the the youngest reservoir units. That's the main problem probably we are going to have here. We have the option for maybe Paleocene, maybe Eocene, and in some areas maybe Oligocene. In the north part, we have a very, very important prospectivity. Here you can see a lot of accumulation charges in the model with oil, and also you have another charge with gas. This part of the basin has oil seeps, has oil coming from wells. Here we have the oil from Perdices, the Perdices area. And then we believe that this is a very, very high potential for the basin. And finally, we have this play area, the eastern part of the basin, where we have mainly opportunities mainly related with oil. That's important from the model. And the other point, the other important point for this area is that we can connect that area with the lower Magdalena Valley. And it is very important, especially for the northern part, because we know the potential we have in the Plateau Subbasin, in the Plateau Depot Center, and that is the only geological province in the area where we have oil coming from fields. Then this northern part of the San Jacinto fault belt represent or has a very good chance for oil. In the San Jorge Basin, that is our proposal for the place. We have one related with the area where we have the gas in Hobotablon. We have options for gas and oil here. And in the southern part, in the area that we call Ayapel, we have option mainly for gas. 90% of these opportunities are related with the gas. Finally, we put everything together and we apply the mass balance calculations method, and we estimate the prospective resource for these basins. In the case of San Jacinto fault belt, those are the results. The oil in place in prospective resource is very close to 5 billions of oil equivalent. And for the San Jorge Basin is something like 0.17 billions. Why we have this difference is easy to explain. It is because here we have huge areas for productive of source rock, and also because here we have at least 2 source rock intervals. We know that intervals, we know the data that we can use for the mass balance. And here we have a small one and a small productive, and also we don't have enough data to predict the quality of the source rock. that's the main points we got from the jet to find, play fairway analysis, and petroleum system modeling. I think maybe we have time for some question. I don't know.
Cesar, thank you. Cesar, I'm sorry, no, Enrique, go ahead, please. I'm sorry.
Okay, we have just 9 o'clock, but yes, I would like to address some of the most important conclusions of this work. But first of all, I would like to say that you see from the previous presentations that this area has a huge potential for hydrocarbons, not just because there's so many hydrocarbons oil tips, but also because there are still some, let's say, underexplored areas. So I will address very quickly, because I know the time is up, some main conclusion. Let's say from stratigraphy, you see that the late Cretaceous and Sinu formation has only been proven to be present in outcrops in the San Jacinto fault belt, mainly in the north sector. Micropaleontology and palynology have clearly shown a Campanian Maastrichtian age, and geochemical data, as Cesar showed to us, from this deposit show properties are very good source rock. On the other hand, late Paleocene, early Eocene, San Cayetano formation has only been identified some wells drilled by the ANH. This unit was deposited in an open marine environment, and towards the bit of Tierra Alta well, the sequence presents excellent properties as a very good source rock. We received a lot of questions, Miguel, and maybe we will not able to answer right now. I suppose we can answer them. There are different type of questions. For instance, Jaime Checa asked us how we recommend how to improve the image that is very bad in the Sinu San Jacinto well, how to improve this image in order to improve the interpretation. Because as you know, San Jacinto Basin and San Jorge Basin has a close structural relationship. Yes, so we need to define some of the questions. But I don't know, it's like a 9:02, so Miguel.
Yes, no, Enrique, unfortunately, we are running out of time, but I just recommend people to put your questions on the chat, and they are being answered simultaneously by our speakers. And regarding the quality of the seismic and how to improve it, Daniel Rodriguez is going to talk about a little bit in our last talk. Thank you, Enrique.
Okay.
Thank you to the Universidad de Caldas. And we invite Freddy to start the talk, followed by the ANH closure. Okay.
Okay, good morning. And thank you, everyone, for joining us today. I just want to make sure that everybody's seeing my screen and listen to me, okay?
Yes, go ahead.
All right, so today I want to talk about some key observations about the shale tectonics in the onshore Sinu Basin in northern Colombia and the implications for the interpretation of structural traps and hydrocarbons exploration. And first of all, I want to thank you, the ANH, in particular Miguel de Armas, for inviting me to give this talk. I'm not sure if you guys are seeing my presentation screen or the other one. Okay, assume. So I always like to start my presentations with the conclusions, so you guys.
Disculpa, Freddy, ¿puedes hacer el cambio? Se está viendo el modo de notas.
Ok, ya lo cambio, sí, ya lo cambio, perdón. Okay, how about now?
Okay.
You should be looking at.
That's right.
Okay, hold on a sec. Sorry, hold on a second, please. There you go. Okay. All right. So again, so I like to start with the conclusion. So basically, what I'm going to try to convince you of today is that the onshore Sinu Basin in northern Colombia is part of an accretionary prism that resulted from the collision between the Caribbean and South American plates during tertiary times. That the deformation is in this part of the basin is mostly controlled by the undercompaction and overpressuring of mobile shales that cause extensive diaparism in the basin, and that's created some interesting structural features that need to be revised using these models. That usually what we're going to observe is boundaries between these synclines that represent mini basins, probably resulted from the mobility of these undercompact and overpressure shales that have been dated about Miocene, Oligocene in age, but we'll talk about that a little bit later. That slow lateral and vertical shale mobilization is well recorded in gross sedimentation. We're going to see some examples of that in seismic. We're going to see evidence of limb rotation, etc. Elements that help us to interpret the shale tectonics in the region. Based on the map, based on the map stratigraphic record on the seismic interpretation across the shale mini basin, it is proposed that shale mobilization began early during the tertiary, during the Miocene, due to shale undercompaction and overpressure, and is active today. So it's not very recent. It started a while ago during the Miocene, probably very early during the evolution of the basin. So I'm going to try to convince you that we don't require overpressure to produce the diaparism, but actually the undercompaction is responsible for the initiation of this process. Now, the amplitude anomalies on the flanks of shale diapirs are common in the basin and could indicate the presence of hydrocarbons. And this is the type of structural trap that explorers should be chasing. And these structural styles and kinematics have a strong impact on petroleum generation and migration in this region. But this has been already mentioned by Cesar Mora in the previous talk. So the shale diaparism is common. It happens all over the world, has been reported widely in the literature, and it happens in both passive and active margins around the world. We have, like in the case of Colombia, examples of active diaparism in active margins, like the South China Sea, where recent oil and gas discoveries have been reported by the China government. We have active shale diaparism in Sumatra and Java Islands in this part of the world. I know we have people from Java connected to this presentation, so welcome. We also have active diaparism in the Makran accretionary prism offshore Iran and Pakistan. We also have, as you know, active shale diaparism in the South Caspian Sea, where we have a large oil and gas province related to these shale diapiric structures. We have reported shale diaparism in Alaska, and also we have this the shale diapir that we're going to review in Colombia. So these features exist in compressional margins, and they are oil and gas prone, demonstrated by these accumulations in these regions around the world. Hugh et al. In 2007 published a paper about how these features can be interpreted, how what is the kinematics and the evolution of these systems. And usually what we observe, especially in offshore basins, is that we observe basically mud volcanoes. And mud volcanoes are these circular features that deform the seafloor that are very common, especially in marine basins, as I mentioned, and they are very common in Colombia as well. When they are on surface, they are very prone to erosion, so they are very hard to observe. But in offshore basins, this is what we see. So basically, we see these transparent zones that we have almost no reflections. In occasions, they're active and deform the seafloor, like this picture on the left. In occasions, they get buried by the sedimentation. So they don't necessarily actively deform the seafloor. But in any case, what is clear from the cases presented in this paper is that most of these features that we observe on the seafloor are just the tip of the iceberg. And these features are usually related to larger overpressure or undercompacted shale bodies that we call shale diapirs. So the features that we see on the surface we call volcanoes, but volcanoes are usually linked in many ways to shale diapirs. And these bodies are the source that feed these volcanoes that are deforming the seafloor. And that mud is transported to the surface through conduits. And that conduits could be faults or could be paleo shale bodies that have been squeezed due to tectonics, etc. We're going to try to see some of these, as we can identify some of these features in northern Colombia. Now, it's very hard to identify the shale diapirs, and it's basically because, especially in seismic, and the issue is because there's no enough density contrast between the shales and the surrounding rocks or the sediments that are deposited on the flanks as these things move. Unlike salt tectonics, where we always see this very sharp contact between the salt diapir and the sediments on the flanks because of the high impedance caused by the high density contrast. This is not the case with shale, and this is why it's very hard to interpret where the actual contact between sediments and the diapir body is. And this is so what we typically observe is these areas that are highly folded. Like see here, we have a series of anticlines and a very broad synclines that are with very large variations in thickness and sequences deposited in these synclines. And then in the between synclines, what we see is these areas of very low amplitude, like no very transparent seismic with no contrast whatsoever. And these are interpreted as shale diapirs. Now, how this evolved, we're going to try to see that. And usually what these are related to is that deep zones where we should expect to find thick source layers. And this is for immature basins. When you have a very mature shale diapir basin, what happens is that thick source starts to disappear because of the mobilization. So eventually what we see is that we're going to find very, very thick synclines that are going down into the stratigraphy, removing this shale layer. So basically that's what we typically observe in areas where we have these shale diapirs. So we're going to try to see if we can find some of these features in the area of this study, which is in Sinu. So we're going to zoom in from planet Earth. We're going to zoom in into Colombia, and then we're going to move into the northern coast of Colombia, where this area of shale diapirs exists. So here we see the Sinu area. Now we're going to show more details about the structural features from a high resolution topographic data taken from an ANH study in 2008. Here we see the topography of this region, where we see a series of synclines with multiple directions. Some of these are northeast, southwest oriented. Some of these are north-south oriented. But you see how this series of synclines that are piled against each other, and we're going to see the interpretation of the geology. So basically, we're going to focus in this region that we believe has been formed by this very active shale tectonics. Okay, so this is the same image now without the animation. Again, here we have this representation of faults that had been mapped based on geologic mapping, surface work done by the Geological Survey and the ANH in the past. And here is the Sinu shale diapir fault belt. This is the geologic map that has been rendered over the topography. Here you see mostly Pliocene and Miocene rocks outcropping. You see how the stratigraphy gets younger as we go north, but there is a large variation in the stratigraphy as you go from one syncline to the other. I'm not going to discuss the stratigraphy at this point. That has been already discussed by the previous group. But what we know is that we have these very large differences between, Pleistocene sediments in some of these synclines. Then you have this very thin Pleistocene sequence here. Then you have Miocene sediments and others. So you have these very large variations in aging and thickness of these tertiary sediments in the synclines, and this is caused by the difference in motion as the shale diapir progress. This is the interpretation of the layering. You can see here the directions of the Please let me know if you have issues with my presentation. I have some comments on the chat, but are you guys seeing the geologic map render on the topography at this point? Can you confirm? Hello?
Yeah, yes.
Okay.
Go
Okay,
ahead, Fred.
Yeah. Okay, good. So sorry. Then, so this is the geologic interpretation again. So here you have these synclines with multiple orientations. Some of them are mostly oriented northeast, southwest, but you see different directions of the axis of this, what we call rim synclines. Here is the mapping of these surfaces that have been mapped as faults. You can see how the faults basically go around the syncline and end on the limits of the syncline. So this feature has been mostly mapped as reverse faults or thrust faults. In our opinion, I'm going to show you that later, we believe these are weld surfaces, meaning that there was a mud that appeared there and now has been squeezed out due to the tectonics. And now what we left with is just these synclines piled against each other. And I'm going to try to explain in a moment how this is formed. Now, this is the position of the shale that appears that had been mapped doing field work. This is as you can notice, most of these mud volcanoes or shale that appears are distributed along the edges of these rim synclines. We don't see diapirs in the course of the synclines, but rather on the limits. And this is an indication, basically, that there was a presence of a large shale province during the formation of these synclines. Okay, so, and then what we observe, these are oil and gas seeps that have been also taken from a regional database from the ANH and the Geological Survey. The green dots represent what seem to be liquid oil seeps. There are some red dots that you can see that it represents gas seeps, and the black dots are undetermined. They have to have a description on the database, but you can observe a lot of these oil seeps towards the east part of this region, and then the seeps become more gassy as you go towards the west. So there is a strong geographic correlation between the location of these diapirs, the edges of those inclines, and the location of these oil and gas seeps, meaning that probably there is leakage of whatever oil trapped or the oil source rock through these diapirs. So basically, this is a seismic section showing what we typically see across these synclines. Even though this has been mapped as a single syncline, as you can see here, there's the seismic line, the position here along the axial surface of this syncline. And nevertheless, we see in the middle of that syncline, this topography, this deformation of the surface created by this transparent area that we have interpreted as a shale that appear. You see the rocks being folded, being on the close to what seems to be the edges of the body. We see evidence of limb rotation. We see evidence of limb rotation on the gross sedimentation, meaning you see this thinning of younger rocks as we go up to the surface, and the decreasing on the depths, suggesting rotation during the formation of these synclines. And that is an indication that there has been active diapirism in this region. And we know that, as you can see, as you go in the middle part of the section, you see the layers getting close to each other. So this transparent zone is now gone. And now they seem to be truncated against each other. So probably that means there was a conduit here of a deeper area of shale, probably down here to 4 or 5 seconds. And that shale has been mobilized through this conduit, forming the diapir. But now that shale is now gone. So all that shale has been squeezed out, moving and has been mobilized to the surface, creating the diapir. These are diapirs are active today. And this is a picture from 2019 in the Sambul volcano called Arboletes. This is a touristic area. People go and swim into these things in Colombia. Fortunately, this occurred very early in the morning, so there was no accidents with humans. But basically, what this demonstrates is that we have these diapirs that are being active today. So this is something to keep in mind. Now we zoom out a little bit, and now we see the we're talking about this province here, the Sinu Shale Fault Belt, or whatever you want to call it. You see here in pink all the mud volcanoes and shale that appear that have been mapped. And that province extends to the north, a little bit offshore on the platform here in the offshore part of the Sinu Basin. So I want to show you a couple of seismic lines from the offshore part, because usually that's where we get the best image quality of these diapir bodies. So this is a seismic section just north of the Sinu fault belt. It's basically the same fault belt. It's just that it's underwater, but it's basically the same region. And here on this seismic line, we observe this very large anticlinal feature, but you see these rocks being truncated each other here in the middle, and then this transparent body on the shallower part of the seismic. We have the formation of the seafloor, so we know that it's a mud volcano. Actually, this mud volcano created an island in the early 70s, and now it's gone because of the erosion, but there was an active volcanic mud volcano eruption in this volcano in the 70s. And we know it's linked to this diapir, but this diapir is floating in the line. We know that there was a conduit that is vertical in this position, probably meaning that there was mud migrating or overpressure shale migrating through this conduit, forming this globe of this diapir. And then because of the ongoing compression, the diapir is gone, and now we have these rocks linked to each other in this part. So this represents basically a welt on where the overpressure mud or shale was mobilizing with. Now, if you notice this green layer here, we believe represent the upper Miocene or the middle Miocene. We don't have well data here, so we don't know what that really is. But above the green layer, we start seeing this this fan of depths, meaning we're having a decrease in the depths of the layering as we go up. That means this layering from pink, yellow, and orange represent gross sedimentation. And the layers from green to the bottom, from green going deeper, are more parallel, more isopac, meaning that these layers were probably deposited before the initiation of the diapir. What that is telling us is that the green layer represents the top of the pre-growth of the shale diapirism. And this is middle Miocene that basically tells us the age of the initiation of the diapirism in this region for this particular feature. And everything else above that was deposited during the diapiric event. And that is very well recorded with the rotation of these layers, the onlap on the flanks, etc. Now, as we change the color of this line, this is the same line. We just changed the colors on the amplitudes. You can see these amplitude anomalies on the flanks. And these are very common in this region. And this probably represent, I don't know, maybe gas or some hydrocarbon on this area. So this become a very interesting place to maybe look for hydrocarbons in this region. What people have done in the past is basically drilling on the course of this. I'm going to show you basically why, because people interpret this as anticlines, ignoring the possibility that then maybe what we have here is a diapir. And nobody has actually, as far as I know, going after these features on the flanks of the diapirs. We also have some stratigraphic features like these maybe channel systems that are deposited on the course of the synclines that might be also a stratigraphic play to go after. But anyway, this is another line close to the previous one. Here we see features like we see the deformation of the seafloor. We interpret a mud volcano in this position, but that volcano is isolated. There's no connection with any nearby mud diapir. But then beneath that, we see this synclinal feature. So that, and this is very strange. And the only way to explain that is that what we have is that probably we have a diapir that was feeding this mud volcano. Now that we don't have enough overpressure shale to keep feeding the volcano, and because of the compression, any mud diapir that was in this position has been squeezed out because of the compression. Now what we are left with is a welt in the area where the mud diapir was present. We have the sediments that were in the flanks now appear to be faulted against each other, but this is not a fault, it's actually a welt. And now we don't have enough overpressure mud to keep feeding this. Then what happens is that this anticline that was present during the diapirism collapses and get inverted and becomes a syncline. And this is what we observe here. Okay, this is called a withdrawal sink due to the lack of additional overpressure shale to keep feeding the volcano. So this is just to show you that this type of structures can only be explained by this process of shale diaparism. Okay, so now from the regional point of view, where are we? This is a regional seismic composed section from the research board done by Mantilla in 2009. Here we have the lower Magdalena Basin that was already presented by Roberto Linares in the previous presentation. We have the Sinu San Jacinto fault belt in this position. And then we have the Sinu Basin with the shale that appears. So this will be in the upper part of the accretionary prism. And then offshore in shallow and deep water, we have the accretionary, the present time accretionary prism in the boundary between the Caribbean plate and the South American plate. So basically, in the regional context is that we will be on a paleo accretionary prism, or the initial accretionary prism, that is now under extensional collapse due to the mobilization of these shales. So the way Mantilla presents the story of this, that we have the initiation of the subduction during the end of the Cretaceous. We have delamination of the oceanic crust. So we have some oceanic rocks going on the overriding plate, the South American plate. And that's why we see some of these oceanic rocks in the edges of the lower Magdalena Basin in places. Then we have the imbrication forming this initial accretionary prism and fault belt with thrust faults, etc., overpressure. And then what we have the initiation in the middle Miocene of the shale diaparism in the Sinu Basin, probably gravitational collapse. And then the prism keeps moving outboard into what we see today in the deep water. And that was presented a couple of weeks ago, or last week, I believe. So this is the compressional model, meaning convergence between the Caribbean plate and the South American plate. There's another model out there that tried to explain the same geometries with a passive margin model. So what they propose is that we have the South American continental cross, we have some transitional cross in between the continental cross and the oceanic cross from the Caribbean plate. We don't have subduction in this model. What we have is just a passive margin and a very large extensional fault that separates the Sinu San Jacinto fault belt from the Sinu Basin and the Sinu accretionary prism in deep water. And the Sinu accretionary prism will not be an accretionary prism, but will be just a gravity-related fault belt, meaning something similar to the West Africa or the Niger Delta model. And so we have these two end-member models, but obviously we have some observations to try to decide which one should we use. So we have GPS data, for instance, present-time GPS data that was published by Smitty in 2015. There are more recent publications, but I don't have access to that right now. But here we see the velocity vectors on the upper picture. It's called A, the velocity vectors relative to North America. So as we fix North America, what we see is that the Caribbean will be moving eastward with respect to North America at about 10 to 20 millimeters per year. And Northern Colombia, with respect to North America, will be having these velocity vectors towards the northeast, north and northeast. And this is the argument for the escape tectonics of Northern Colombia. And that's fine, relative to North America. But as we want to understand what is happening between the Caribbean and Northern South America, we need to fix the Caribbean plate to see what the velocity vectors in South America are doing. So that's the figure at the bottom, figure B. So here we fix the Caribbean plate. Now you see the vectors in San Andres and Providencia Islands are now 0. They are not moving. So we fit the Caribbean plate. We now see North America moving towards the west relative to the Caribbean plate. And look at what happens with the vectors in Northern Colombia. The vectors turns towards the northwest, meaning that Northern South America is moving towards the northwest with respect to the Caribbean plate. And that means convergence in the plate boundary. So, and this is the predicted relative plate motions along those plate boundaries to fit these two observations. And the solution of these guys is that we, at the plate boundary, we need to have convergence. And the convergence decreases as we get to the north, because here we have abstractly motion. But in the area of the Sinu, we had the convergence is about 6 millimeters per year in the plate boundary. So we had convergence from that. Now, if we do a plate tectonic reconstruction like the one that has been done by Boschman et al. In 2014, what we observe in this region is that this is the Caribbean plate, this is South America, this is North America. We're fixing North America in this reconstruction. We see the Caribbean plate that was created in the Pacific. It starts moving in the gap between South America and North America. This is the blue will be the present time Caribbean plate. This gray area will be Paleo-Caribbean plate that now has to be somewhere. At this point, at about 60 million years ago, South America started moving to the north with respect to North America. The Caribbean plate keeps moving east, and this gray patch here is going to start being subducted beneath Northern South America. And this model predicts that about 1,000 kilometers of Caribbean plate had been subducted beneath Northern South America and is actively convergent today. So what we have seen from papers like Van Helmen in 2015 that published a very interesting paper talking about tomographic data to look at the boundaries between plate tectonics. This is a section that was published in that paper. Here is Northern Colombia, here the Santa Marta, Sierras, etc. Here the Caribbean plate, Cuba. And you can see here in blue, this anomaly beneath Northern South America, which is about 1,000 kilometers long. And this will be the Caribbean plate going beneath Northern South America. It's flat subduction close to the boundary, but then it starts getting deeper, and with a higher dips in what is called the Bucaramanga nest today. So there is strong evidence, or at least seismic evidence, of that subduction beneath Northern South America. So this is a convergent margin, not a divergent margin. Okay, so let's look at the details on the Sinu Basin. I'm going to show you the seismic section. This is the seismic line, showing basically what we see in some other areas in the Gulf of Mexico and in other places. These transparent zones here, like this area there, and they're bounded by or limited by these synclines with very variable stratigraphy, a series of unconformities. You see this decreasing depths of the layers as you go up, suggesting rotation during the formation of the synclines. Here we have another transparent zone. Here we have another transparent zone. Now, the previous interpretations in this region was that in the areas where we don't see anything or we have very poor seismic data, we're basically filled out with faults and imbrications. So very high steeping beds in anticlines with reverse faults and highly imbricated areas. Those areas will be the areas where we don't have any data. But we know, based on what is outcropping on the surface, that there are mud diapirs or shale diapirs in this region. So I have a student doing an undergraduate thesis in 2015, Juan Sebastián Eslava, who now works for CEPCO. And this was the same seismic line. And we decided to interpret these areas of like no amplitude or very transparent seismic areas as mud diapirs. And this is the same line, but with a different interpretation. So we have the anticline. We obviously honor the outcrops of the mud diapirs on surface. Sarah, I'm running out of time, but anyway, so this was his interpretation. We see the variability. He was able to map the high variability on the edges of the stratigraphy across the synclines. So for instance, in this case, there's no repetition of the stratigraphy. We had a very Jones syncline in between two very old synclines. And the only way to explain that is doing shale tectonics. So he did a reconstruction of this, a sequential reconstruction. So we're gonna go back in time. He did a sequential layer by layer reconstruction. And then what happened is that he was, because of the reconstruction, some holes started to open, and the only way to model that was filling out with shale diapirs. We keep reconstructing this and so on and so forth until we get to the point where he predicted that about 4 kilometers of shale were needed that started to form these diapirs. So as we do a forward model of this, starting at 24 million years ago, we start seeing these two layers deposited about 60 million years ago. Because of the change in thickness, and the reconstruction predicts that you require some folding, early folding occurring, like probably detachment folding, to explain these geometries, because you see this unconformity. We have a period of time about 14 million years ago. We know 14 million years ago, we know the formation, and then after that we start having the shale diapirism, and then forming these very Jones synclines or rim synclines on the edges of these diapirs, and some of these diapirs finally get disconnected from the main source, and this is the geometry that we see today. Now, what does it look regionally and in the context of the Caribbean of the accretionary prism. This is a seismic line. This is a display 1-to-1. This is a line to the north, and then we're going to see the line to the south that connects the offshore portion with the Sinu Basin. So here is the seismic interpretation. This is a 1-to-1 section. We're going to start moving to the right. We see the imbricate system with a series of shear fault and faults forming wedges on the frontal part. Then we see this imbricate system with multiple detachment. We have a deep detachment here, a shallower detachment in the middle part, and then we get into the platform and into the coastal areas, and on the onshore areas, we start seeing this shale diapir province, where we have this series of what look to be normal faults, but they're not normal faults, they're actually wells. So meaning that probably there was some diapir here that has been squeezed out because of the compression. And we have the formation of these very large anticlines with truncated beds beneath this large multi-diapirs. The next time section shows the position of the Chronos well, where a large gas province, methane gas province has been discovered. And we're going to start moving to the east. This is also a 1-to-1 section. So here we don't have the back truss from the previous section. We just have the frontal truss with the same deep detachment with the tertiary rocks being deformed. These are all shear fault and faults related to mobile shales. Then we get into the onshore portion with the areas where we have no information, but then we get into these rim synclines with mud volcanoes, mud diapirs, etc. So this is just to show you the context of the position of the Sinu Basin with respect to the accretionary prism. What is the best analog that we had found? Because there's no much research going on this area in Colombia. So it's hard to say how these systems evolve. And this is something maybe somebody's interested in doing research of this, there will be a great opportunity to do so. But we found that the Macron accretionary prism is very similar to what is happening in Colombia. So the Macron accretionary prism is located in the limit between the Arabian plate and the Eurasian plate. And the convergence between these two plates, there is an accretionary prism offshore Iran and Pakistan. This is a regional cross-section published by Berg in 2018. This is a seismic section. You see the accretionary prism. And then up on the platform, we have this shale province extensional area, which is basically gravitational collapse due to the mobilization of these shales. This is a cartoon on what the geology looks like in the shale province. But if you look at the surface geology, it's very similar to the Sinu, with these rim synclines, elongated in multiple directions, pile against each other with very tight anticlines, and always mud volcanoes and shale that appears in the course. Now, this has been modeled mathematically to try to explain how these things are formed. Ruth et al. In 2018 basically modeled when you start producing contraction on these sequences that are highly undercompacted and then highly overpressure in these areas. So what you observe in this region, which is, I'm gonna go back to the animation. When you start having compression, you start forming the accretionary prism, then you have deposition of the highly undercompacted beds, and then you start having more sedimentation on these undercompacted shales. What happens is that these shales start to mobilize due to the compression, and then you start forming these rim synclines with gross sedimentation. Then you get the tone of these diapirs squeezed out because of the compression. Then what you are left with is this series of pile synclines or rim synclines against each other, and then all these shales and undercompacted shales are now gone because they have been mobilized. And that, let me put it again, explains basically how the Sinu fault belt is formed. So this shale diapirism, early shale diapirism, due to the undercompacted sediments, the loading of this gross sedimentation creates the overpressure. So there's a positive feedback that forces the system to keep mobilizing and keep producing these synclines, shale diapirism, mole volcanism, and then the accretionary prism moves outboard in what we see today in the offshore port of the Sinu Basin. And this looks a lot like the Sinu onshore that we see today. So this is a good way to explain how the Sinu fault belt was formed. And I go back to the conclusions that I already summarized on the first slide. And thank you for your attention. And please visit our website, geostrap.com. This is a work that has been completed independently with public data. And again, thank you to the NH for the invitation to present this work.
Thank you, Freddy. Daniel, please.
Okay, thank you, Freddy. Thank you, everyone, for this great presentation. And now I'd like to share with you some of the things that, based on these models and what we see in seismic, we have identified for some sort of place. So just give me a second, please. Okay. So this, as a part of the Colombia round 2021, is the Sinu and Jacinto exploratory opportunities. First, we're going to show the location of the blocks that we are offering during the round. Afterwards, we'll see some of the history of exploration in the area that we are studying. Some information about the database, the infrastructure nearby, the geological framework that's been quite well explained by Andres Pardo and Freddy. The well summary of the couple of wells, so around 7 wells that are in the area, but most of them don't have information because they're quite old. Some of the seismic interpretation that we have performed in the ANH that we have carried out, and the prospectivity. Is some basic prospectivity, is a first glance of prospectivity in order to try to understand, or at least have a first glance of what we could expect if we make some assumptions based on the mood diaparism that Freddy showed before. So as an introduction, the location, the blocks that the ANH is offering during this Colombia round 2021 is the Sinu San Jacinto 1-1, the Sinu San Jacinto 1-2, the Sinu San Jacinto 7-1. The first one has an area of 135,700 hectares. The second one has an area of 126,900 hectares. And the last one has an area of 2,700 hectares. Those blocks are located in the departments of Antioquia and Córdoba. So first, take a glance of the history of exploration in the basin, that despite of being underexplored, because we only have 2D seismic, the 2D seismic is not considered with good quality. We don't have maybe the seismic coverage that we will expect with some wells that have been drilled. For example, the Aguas Claras wells were drilled in 1926. And we got as well the Flores Santo field, that was the first field into the area that was drilled during the 1945. One well with commercial production was Flores Santo 1. It was depleted after 2 years with a total production of 28,730 barrels of 51 API, means light oil. As well, we got Jaraguay Norte 1 that had production of 126 barrels of oil per day with an API of 48 degrees. Those couple of fields are nearby to the area and are an important analog in terms of what we see in the seismic, in Flores Santo, in Jaraguay, and what we could expect in the area that we are offering. So successful production test in another 13 wells, and most of the wells were considered as not non-commercial at the time. Something that's quite important to mention is that those wells, as we got a light oil, of course, they found gas as well. But at that time, for example, at the time of Flores Santo, 1945 and 1947, as well as Jaraguay Norte, the gas was considered as something that was not interest for the company that were drilling. So now maybe we can think that maybe that gas could have some commerciality. And as total for the area, we got 191 wells that have been drilled in the whole basin. So this is a bit about the database. We got the wells and the fields nearby. We got in the areas and nearby to the areas, a total of 8 wells. Most of them don't have information because maybe they are quite old. And as well, we got the field Flores Santo and Haraguay Norte. It's important to take into account that maybe despite the fact that Piedrecita and Porquería have a total depth of 12,000 and 14,000 feet, they don't reach some of the main reservoirs, maybe because of the location, and as well as the Flores Santo and Haraguay. So talking a bit about the seismic, we got in the area 8 seismic surveys that got a total length of 3,101 kilometers. Most of these seismic surveys are considered that they'll have a good imaging, and that's one of the questions that have Jaime Checa. And I will show afterwards that maybe it's not that the seismic image or the seismic quality is not good enough, is that maybe we are trying to see some things that doesn't exist. And as you know, sometimes for having a good model or for having a good processing, we need a good velocity model, and we have maybe, if we got available, previous geological interpretation that help us to maybe to estimate what we could have a way or how we can improve the velocity models. Without that, it's hardly, or it's quite hard to find a good image or trying to have a good processing. This is the infrastructure. We got an oil pipeline quite close, 107 kilometers is the Terminal Coveñas. As well, we got 3 stations near in the gas pipeline, is the Montería, Pobo Tablón, and Cerro Matoso. Let's talk a bit about the geological framework. So first, I would like to share with you some of the Bouguer anomaly and the general structural elements. Why it's important to have the Bouguer anomaly as shown by Roberto Linares and interpretation. It's because of the multi-aphorism and the chaotic reflections that most of the time we cannot see the basement. To see the basement and to model the basement into the seismic lines is sometimes impossible. So taking into account the information of the potential fields, such as gravity and magnetic, we can easily, or we can integrate a complex model, taking into account this information to have a best estimate of what the depth of the basement could be. We got a couple of local depot centers in here. We got a positive anomaly that is in here that's representing the San Jacinto fault belt. And we got as well some regional depot centers, and this one in here, between the difference between the positive anomaly and the negative anomaly is related to the Romeral fault system. To talk about the stratigraphic setting that Andres Pardo has already showed to us, we got here some the comparison between the San Jorge Basin and what's happening to maybe most of the what are considered the reservoirs in the area of the Sinu, that we got Uraba, that got its fluvial phases in both of the sub-basins. We got the Porquero that got its equivalent in the Sinu San Jacinto, that's called the Flores Santo Formation. It's quite important to take into account that the Flores Santo Formation is going to have deeper phases than the Porquero Formation. And as well, we got the Ciénaga de Oro Formation that is going to be related to the Pavo Sandstone that is considered as well a reservoir. So the deepest phases to the ones related to the Porqueros already said will be found in Flores Santo Formation, and sandstone of deeper phases to the ones related to Ciénaga de Oro are known as Pavo Sandstones. We got to take into account as well that if we are going deep into the environment, we have as well maybe a thinner sandstones that are some important facts to take into account at the moment of modeling the reservoirs. Freddy already talked about the structural framework that we got the model from Mantilla Pimiento. So 3 major tectonic areas were identified into the composed seismic section. And as well, so we got 3 different ones. The first one is an active accretionary prism with a seaward virgin imbricate thrust system that is going to be the one related to the Sinu offshore. We got as well a fossil accretionary prism, including the Sinu accretionary wedge and the Sinu San Jacinto fault belt that's characterized by broad folding, multi-aphorism, and normal faulting, as Freddy mentioned, that is likely to be due to gravitational collapse. And the last one is in the lower Magdalena Valley, that is the San Jorge plateau for arc basins. So talking about the mode diaparism that has already been shown, I like to maybe focus on how the mode diaparism in some analog to the salt, despite the fact that the salt have some different properties in terms, for example, of seismic imaging, that the salt have a lower density than the mud and has a high velocity. But either way, the mud diaparism and the salt diaparism have, in terms of a structural setting, have some sort of related features. So mud diaparism could be explained based on salt diapers schemes due to its similarity. Into the raster, we can find some ellipsoid structures in surface that are related to smooth diapers and syntectonic synclines. The syntectonic sediments could be identified because of its difference in thickness, welt faults, that are the faults where the material being salt or being mud was present, but due to its mobility is now not present, and it's making a juxtaposition between some sediments. In the Sinu and Jacinto mud diapers have a strong relation with oil and gas seeps distribution. That's quite important because it may be acting as two sort of elements into the petroleum system. Maybe the first one as a migration path, and the second one, and we expect that is going to act as a seal as well. So we have some traps associated to diaparism. For example, we got source to structure maps. We got trap formed by fault sealing. This one here is quite important. That is a trap formed by diaparism on two flanks. And as well, we can have trap formed by fault sealing. As far as I remember, I think Ricardo shown a couple of traps like this. And here I'm going to show about the well summary and analog fields. I'm going to talk about the Santo and Harawai and some seismic interpretation in those couple of fields. So first, talking about Santo, 12 wells were drilled from May of 1945 to August of 1947. Most of them were drilled by Soconomobile and classified as producer wells. However, formal production was only declared in the wells Santo 1 and Santo 6. Here's the location. We can see here the seeps that are mapped quite close to the field. It's important to remember that all of those wells were drilled previous to have some seismic data that allows to understand the system. 10 of the 12 wells were shallow, an average of 1,500, and two other, the Santo 1 and the Santo 10, reached a total depth of almost 7,000 feet, as well as 11,000, respectively. Santo 1 have an oil production from the Santo Pajuil formation between 694 and 614. That was the interval that they tested, and started production in December of 1944. To August of 1945, the well had produced 28,000 barrels with 51 degrees of API. This information was taken from Ecopetrol 2000. And Santo 6, during test, the well produced 42 barrels in 12 hours. That was during a short test. Here we got the interpretation, our interpretation of the ANH, trying to understand how the Santo well, how the Santo field is related to the mud diapers. So we got here the syntectonic synclines, and we can see that Santo, the sediment Santo took, is from a flank that is against got an overlap to the mud diapers. The second one, or the second field, is Harawai Norte. Harawai area is located out the south of the Sinu Basin. At the Harawai area, rocks from Oligocene, the Maralú Formation, that is an equivalent of the lower Ciénaga de Oro, to the Pliocene, the Corpa Formation, have been drilled. Well targets were the equivalent of the lower Porquero Formation, Santo Formation, and Ciénaga de Oro Formation, the Pavo Sand zones. Total depths of the Harawai Norte wells were reached between 2,500 and 5,000. The well Harawai Sur one reached 8,000 feet in depth. Oil found in production, test, and seeps in the area are considered as light oil. the Pavo sandstones are considered as the best reservoir in the area. The well Haraway Norte 1, during production tests in the Flores Santo formation, showed 3.5 barrels of 48 degrees of APA. Oil were obtained at the interval between almost nearby to the 2000 in depth, and 6.3 barrels of 47 degrees of API were gotten in the interval between 1100 and 1300. The well produced at its peak 127 barrels of oil per day. Haraway Norte 3, doing tests, only showed 1 gallon of oil. This is the location. We got the same ellipsoid structure. We got the same sort of seeps, and we got the location of the wells in some sort of same position to the ones found in the Flores Santo field. Here is our interpretation of the location of the Haraway Norte field related to the mud diaparism and the possible sediments that are Flores Santo formation and the Pavo sandstones that are considered those sediments. We got as well some normal faulting that is going to be related to the gravitational collapse. And this is the location. We got as well a trap that is against or that are overlapping against the mud diapirs. So this is one of the important topics about the Sinu San Jacinto is the seismic quality. So in terms of seismic quality, we got here some reflections that, in my opinion, could be improved. However, the point is like we got what is called chaotic reflections of anticlines, and maybe most of the people that have interpreted the Sinu San Jacinto area in previous stages maybe complain about that we cannot see the anticlines. Why we cannot see the anticlines is maybe because there are no anticlines. Maybe because these chaotic reflections that in terms of seismic quality could consider as bad imaging, maybe they are showing what should be there. It means that mud diapirs with chaotic reflections, because if we take a look into the chaotic reflections, they got some sort of geometry. And if we interpret that geometry and we use 3D models to use that chaotic reflection, we will see that they can show easily the coincidence between the mud diapirs that have been mapped into the geological maps and where we got in the seismic. Here, into the syntectonic sediments, we got well-defined reflections. Here as well, we got the chaotic reflection at the juxtaposition of two synclines. Maybe we got a well spot in here. And we got well-defined reflections. So this was the question, how to improve? How can we improve the image into the Sinu San Jacinto Basin? So historically, getting well seismic imaging at the Sinu San Jacinto Basin has been always considered a challenge. Geophysically speaking, it is probably that the image is correct and the anticlass does not exist properly. Mud diaparism is controlling strongly the basin, and its seismic signature is dominantly chaotic reflections. As I said before, chaotic reflections have well-defined geometries that matches with surface geology. So what we propose, maybe we got an example of salt diaparism that, as I've mentioned before, despite the fact that it got different properties as velocity and density, we can see in the image that we have in this moment that there's a contrast between the mud diapirs and between the sediments. So what we propose is first take into account the mud diapirs into the reprocessing into the velocity model. Try to use that, maybe try to use a full waveform inversion to have a velocity model.
The RTM that is called reverse time migration. So it could be a tool to improve the imaging. We got here the high resolution top the side of the image that we can share with we can compare with the mud diaparism, and using reverse time migration, that is a sort of technique, what is called wave-based migration techniques, maybe we could improve that image. So my recommendation as geophysicist for this part of the area is try to take into account mud diapirs at the moment of the reprocessing. So we're going to show the seismic interpretation with 3 different types of traps. The first one are traps on flanks. The second ones are some sort of anticlines with normal faults by collapse. And the third one is some sort of unconformities. The first one, this is an interpretation at the first block. We got in here the mud diapir. We got in here how the sediments are related to that one. And maybe we can think that maybe in here in the anticline, and we can see some bright spot in there, maybe it's related to light oil. And that as well in here, because of the geometry of the body, we can have well traps for the sediments that are in this area. So this is the analog that we are trying to show for the leads that we have mapped in the first area that we are offering the Colombia round 2021. This is the second one that we see an anticline at the second area. This anticline is as well related to mud diapirs. It's some sort of turtleback structure. However, it's some sort of antiform that is formed in the early stage of the dynamic of the mud diapir mobilization that is going to be called residual height. And we got this sort of trap that is quite similar to the anticline that maybe we are seeing here. We got a third one that we can see the difference between the growth strata related to the scene tectonics and the mobilization of the diapirs, and we got a non-conformity in here, assuming as most of the diapirs of the diapirism that take place in the Sinu offshore, if we think that the mud diapirism is of Oligocene times, so the unconformity will be previous to that one. And I have maybe interpret some sort of imbrication that we got previous to that unconformity. So maybe that imbrication and maybe some sort of traps that are formed naturally by the unconformities could be a sort of trap that is worth to take a look at. We got a final interpretation that we got possible traps against mud diapirs. We got in here the mud diapir, we got here the syncline, and as well as shown in the first area, this one is the third one, we can have traps related to the 2 flanks to the diapirs. So at the first glance, we have estimated some recoverable prospective resources. For the first area, we have identified these 5 leads. These 5 leads were identified using seismic and surface geology, taking into account the raster and the distribution of the ellipsoids and the seeps. So we got in here 5 leads with areas that are nearby from 20 square kilometers to 30 square kilometers, and prospective resources between between 9 millions of barrels to 21 millions of barrels of oil. Those are recoverable prospective resources. Those are risked. We got the second area. We got as well same leads. Those leads in here, the 8th one is related to the anticline that I've shown, and the 12th one is related to the stratigraphic traps that maybe are related to the unconformity, or maybe the thrusting that we have seen previous to the unconformity. Here as well, we got 5 different leads that range in area between 4 square kilometers to 21 square kilometers. Oh, sorry, between 6 kilometers and 45 square kilometers, with a prospective resources between 4 million barrels to 30 million barrels. Of course, I got to clarify that this is a first approximation that we got to the maybe prospectivity of the area. However, it's left to take to acquire some 3D seismic to improve the models of the mud diapirs, understand what's the quality of the reservoir, and try to understand the spatial distribution of the reservoir. And this is the last one. We got 5 leads in here. We go from areas from 20 square kilometers to 45 square kilometers with prospective resources from 13 millions of barrels to 30 millions of barrels. This is the total prospectivity. We have found into the areas 13 different leads with an original oil in place of 1,282 millions of barrels. That's the first approximation. We use a recovery factor of 50% because of the light oil, and a chance of success of 30%, taking into account that Flores Santo, Paraguay have proven the petroleum system, and we got seeps all over the area that are showing that effectively we have some sort of liquid into the area. For this, the best estimate is around 641 millions of barrels. These calculations were deterministic. We use a porosity of 17% and a net pay of 60 feet. So conclusions for the area. The area, despite of being unexplored, has a very long history of exploration, including wells of the Flores Santo field, drilled from 1945 to 1947 by Soconomóvil, and wells of the Paraguay Norte field, drilled in 1981 by Petroleum. 7 wells and 3,101 kilometers of 2D seismic have been acquired in the mega area, including the 3 blocks that I have already shown. Maralu of Eocene, H, and Canzona from the upper Cretaceous formations are considered as the source rock in the area of Pavo Sandstones and Pavo Sandstones, Flores Santo, and Pajuil formations are considered as the reservoirs. The synclines and main structures in the area are dominated by the dynamic of the mud diapirs, with a source possibly at Oligocene sediments. 2 fields have shown production in the area. The first one was Flores Santo, and the second one was Paraguay Norte, with 12 and 5 wells drilled respectively. The seismic imaging could be improved using wave-based migration techniques, such as reverse time migration. As I showed you, 3 different surface traps have been identified: traps of mud diapers flanks, anticlines with normal faults by collapse, and the third one, traps related to unconformities, being the first one the most common. Inside the areas offered by the ANH, 13 leads have been mapped using surface geology and seismic interpretation, with a best estimate of recoverable prospective resources of 641 millions of barrels. Thank you for your time, and I'm sure that there will be a ton of questions, and I'm happy to answer them.
Okay, thank you, Daniel. Thank you, Freddy, and the Universidad de Caldas. Well, we are running out of time, unfortunately, but I saw that a lot of questions were answered directly through the chat. I'm glad to see that. I was glad to see that. Just to remind you that the GeoVisor, which is the map that illustrates all the blocks in the country that are being offered by the agency, is going to be loaded this weekend. So as I mentioned at the beginning of the talk, unfortunately, we have been unable to put all the information in our web page, basically because we are facing that situation with the blocks in the Caribbean Sea. But we are going to omit those specific areas, and we're going to load all the rest of the information in the country. All the blocks that are being offered by the agency are going to be located in that GeoVisor, and it's going to be available starting this weekend. The presentation that were presented today are going to be loaded as well, with the exception of the Freddy Corredor, that the one is not going to be included, only the one from the university, the Caldas, and this last one from the agency. Okay, gentlemen, just to mention to you our next talk, Jesus, our next talk we're going to take place next week, and we are going to have the Choco mega area, and we are going to the 2 speakers at this time. We're going to have the National University with the Geological Integration Evaluation of Oil Systems and Prospectivity of the Tumaco San Juan Foreign Arc Basin, Northwestern South America, and we're going to have the summary of the agency as it's going to be included in all our talks. Just to remind you that we will have it on May 7th, the lower MAC, May 14, middle MAC, and we will have Ivan Olaya invited for that one, the middle MAC. by Upper Mac, May 21st, Llanos, May 28th, Pacific, June 4. We will have Ivan Olaya as well invited for that one in the offshore. And June 11, we will have Cauca Patilla, June 18, Caguán, June 25th, Cordillera Oriental, Eastern Cordillera, July 2nd, Catatumbo, July 9th, Guajira, July 16th, Guajira, I'm sorry, July 9th, Guajira onshore, July 16th, Guajira offshore, July 23rd, Tumaco, July 30th, Putumayo. Okay, gentlemen, thank you very much and see you next week. Thank you for attending this talk, this workshop. Bye-bye.